Thank you so much for having me. It's a great pleasure to be here. Just out of curiosity, how many of you are residents? Oh, okay, good. And how about specifically neuroradiologists? Okay, and then general radiologists or other radiologists? Sorry, I don't know what I'm lumping into. Okay, so a good mix of people. So I wanted to talk about diffusion tensor imaging in brain tumor imaging. Primarily, I'm going to talk about diffusion tensor imaging, but I think we need to know some things about diffusion weighted imaging in general, and then we'll move on to DTI. So, of course, famous Albert Einstein, he's the one that described Brownian motion, which is the random movement of water molecules in an unrestricted medium. So water tends to just kind of move. You know, if you put a little dye color into a bucket of water, then the water molecules are going to move in a random way, but eventually they're going to spread into a sphere, right? And then that is affected by temperature, time, and the type of medium that's in there. And diffusion weighted imaging, to make everything extremely simple, is you're just trying to measure how big that movement is of water molecules within essentially a voxel. So the equation for diffusion weighted imaging is the signal that you get at some point is equals to the original signal, and then to the exponent of negative b d. And d is the diffusion coefficient, which means that the larger it is, then the signal will be essentially lower. And then the b is the diffusion encoding gradient, strength of your b value basically. And S0 is the equivalent of your B0 image. So you have your signal at some point is equivalent to your B0, and then all that other stuff about the diffusion gradients, how long you wait, or the apparent diffusion coefficient, the inherent properties of the water molecules. And when you try to get to the ADC map, all you're essentially doing is you're calculating 3 different directions, and then when you take the cube root, then you end up with your ADC map. And then again, the summary is that you get information about the magnitude of the gradient, okay? Just how much water molecules are moving. The trace image, like I mentioned, just contains T2 information because that signal is equal to the original signal, which is the B0 image. And the B0 image being T2 weighted means that you have information of T2 effects in there, which is why you get T2 shine through, right? And what you can do is actually get rid of that T2 effect by dividing some things. And this is not the actual division here, but what you're trying to do is to divide your diffusion weighted image by your B0 image, and then you'll end up with the exponential function. So I don't know if you've seen actually these exponential images when you're doing imaging, diffusion weighted imaging. No, you guys don't get that image. So your ADC map, if it's dark, it restricts, right? If it's dark, it means that there's restriction going on. Your exponential image is the opposite of that, but it also shows you true restriction because the B0 effect is gone. You just divide your signal by your S0, and you're left with the exponential function that I showed you earlier. And you're left with a positive diffusion restricted image. So if it's positive on the exponential image, it means that it's actually restricting. In reality, we don't really actually use this that commonly because I think the signal is not as clear as your ADC map. But in challenging cases, you can use that exponential map. And again, this is all just background until we get into your diffusion tensor stuff. So you're taking 3 different gradient directions, right? And there's 2 concepts here. One is called isotropic diffusion, and then the other is called anisotropic diffusion. So in isotropic diffusion, what happens is, like I mentioned before, this is what Einstein described, is water molecules are randomly moving in an unrestricted medium, so it's going to spread out into a sphere. In anisotropic diffusion, what happens is that there's a restriction. So let's say you have a huge column, right? The cylinder, like a cylinder, narrow cylinder, but it's really, really long. Obviously, what happens is that your water molecules are going to be somewhat restricted going sideways, right? Because it's kind of narrow. But it has unrestricted movement up and down the column. So this is called anisotropic diffusion because it tends to go not in a circle, but in 1 or 2 different planes. And when you actually acquire your diffusion weighted images, depending on which direction you're getting at, you end up getting that information in your actual source images. So if if it looks like nothing is moving, it means that the gradient has not interrogated that direction properly. To get into diffusion tensor imaging, so instead of looking at the spread of water molecule and just the magnitude of it, right, because that only gives you information on how much the water molecule is moving, we can actually use more gradients. So if you use more than 6 gradients or more, it turns out that instead of getting a sphere, you can get a spheroid, ellipsoid shape. And when you get an ellipsoid shape, now you're getting information about water molecules moving in 3 different directions, right? X, Y, and Z. And so this is the basis of diffusion tensor imaging. And what we need to do is to solve 6 equations to get those 3 numbers, okay? And we don't need to get into the mathematics of this, but basically this is kind of how it goes. And if all the eigenvalues, which is the direction that the things are going, we have 3 eigenvalues here, X, Y, and Z. If all of those are equal, then that means that it's a sphere, right? X, Y, and Z, if it's all the same, then that's a sphere. If one is much, much, much larger than the other 2, then you have a cigar shape. It's like a cylinder. Or if you have 1, which is equal to 2, if you have 2 that are much, much larger than the other one, then you have a pancake shape, if that makes sense. And when you look at voxel level, then this is the representation of what you find in diffusion tensor imaging. So some of these you can see are relatively, I don't know where my mouse is, but some of them you can see are relatively round, right? If they're round, then that means that the eigenvalues are all equal. It's a sphere. If some of them are really directional, that means that the water molecules are moving in those certain directions. Yes? So now the beauty of this is not only do you get information about how much water molecules are moving in 3 different directions, but you can also calculate the direction, right? Because you can see some of these look like they're pointed up, some of these are looking like they're pointed sideways, etc. So when you code those, when you say like, okay, all the stuff that's moving up, so anterior to posterior, let's call that green. And everything that's moving sideways, let's just turn that into red. And everything that's moving cranial caudal, let's turn that into blue. So one of my fellows actually had a really good way of trying to remember this, is sideways is stop, so that's red, okay? Anterior to posterior is go, so it's green. And then superior to inferior, cranial to caudal, is blue like a waterfall. So beautiful way of trying to describe that. And now what you can do is if you try to connect these lines, then you end up with brain tracts, because what happens is there's a lot of bundles of white matter in the brain that are organized. And if you start from a location and you ask it, okay, can you just try to get along the lines that we made and then just stop whenever you want to stop, then you get these kinds of pictures. So I don't know if you can do cross-eyed images, anybody here, but you know, this is actually a 3D image. So if you use those books that you used to have and then things jumped out at you 3D, yeah. If anybody can do that, it's kind of neat over here. So I'll give you a few seconds to do that. No? Anybody got it? Ah, see, that's awesome. Great, great, great. Okay, so, and then this is, for example, you can isolate some tracks. So you say, I'm going to put a region of interest in part of the brainstem that we know the corticospinal tract goes through, and these are all the fibers that represent the corticospinal tract. So, practically speaking, diffusion tensor imaging had a lot of promise in neuroimaging, because the one thing is you can actually calculate numbers that are that give you much more information than just regular diffusion weighted images. So you have your anisotropy, which is your fractional anisotropy. There's a bunch of other metrics you can use. The problem is that in practical use, I haven't found DTI to be really that useful for that kind of stuff. Like there's tons of things in the literature about, abnormal DTI in trauma or like brain tumors itself, or like seizure patients, et cetera, but it's really hard to get correct numbers across institutions. But there are 2 instances where I have found this to be helpful, and this is what we're going to talk about. One is for pre-surgical brain mapping. So if you have a brain tumor, surgeon needs to get in there and take that tumor out, then what do they need to do to try to avoid some of the white matter tracts, okay? And then like important white matter tracts, like for example, the corticospinal tract, which is responsible for your movement, hand movement, leg movement, all that kind of stuff. If the tumor is close to it, but they don't know it, then they can inadvertently cut it, right? So you want to show them where that cortical spinal tract is so that they don't mess around with it. The second thing, which we'll probably end up talking about more, is pathway of glioma infiltration. So you got your high-grade gliomas or infiltrative gliomas, and it turns out that these gliomas want to spread, not all the time, but often, along these white matter tracts because it's kind of easy to get to these locations. So let's say you have a lesion in the occipital lobe, right? The tumor can spread locally, but it can also spread along the optic radiation, for example, and get in front into the thalamus. So that's a really simple concept, right? But what I do with my residents and fellows is that a lot of them don't know the anatomy of the white matter, and this becomes really important. You need to know white matter anatomy to try to figure out where that tumor could be. And we have had countless cases, which some of them I saved, so I'll show you one or two of them, that we were able to find distant lesions just because we knew white matter anatomy. So this is basically the primary point of this talk. DTI for pre-surgical brain mapping, again, to try to show the neurosurgeons, what things to avoid. In general, we're looking at motor, visual, and then some language things. So for motor, it's the cortical spinal tracts, which I'll show you. Visual, optic radiation. And then language is really complicated, because I think a lot of people know that the arcuate fasciculus, right, goes from Wernicke's to Broca. That would be one of the primary language related regions of the brain. But there are many, many other white matter tracts that are also related to language. So the arcuate fasciculus, which I just talked about, of the dorsal stream. Nowadays, a lot of people are talking about the ventral stream, which are additional language related white matter tracts. The uncinate fasciculus, the extreme capsule, inferior frontal occipital fasciculus, which goes from the frontal lobe to the occipital lobe, inferior longitudinal fasciculus, which is from the tip of the temporal lobe back to the occipital lobe, and then the middle longitudinal fasciculus has been described in animals, but we haven't really been able to do it too well in human beings. So I don't know if this shows up too well. So this is DTI for pre-surgical brain mapping. So the important tracts that I was talking about here. So the blue in the blue arrow is your cortical spinal tract. So that's the one that you want to pay attention to. The green on that same image there, is there a, I don't know if there's a, what you might call it, that thing? Laser pointer arrow? No, that's okay, I'll just describe it. On the bottom left, that would be your optic radiation, right? And then, mouse? I don't think my mouse is connected to this, so. No. Yeah, that's okay. So your optic radiations, and on the left side, the arrow on the other side is your temporal occipital. So it is your inferior longitudinal fasciculus.
Just put this.
Oh, thank you. Oops, sorry.
אפשר עוד חושך? סתם, הצלחת?
Thank you. Thank you, thank you, thank you. Okay, we'll see if this shows up. And then the arrow that is more medial is your, I guess the mouse is not here either, is your inferior frontal occipital fasciculus, okay? So, cortical spinal tract, optic radiation, inferior frontal occipital fasciculus, and then inferior longitudinal fasciculus, okay? And on coronal images, we're going to find some additional tracts that are important. This is going to be complicated. All right, I'm just going to talk loud. This is your...
This is
Yeah, it's...
no, this one?
But we have a
Yeah. I thought somebody had a pointer.
No, we have the pointer. Where is this?
Wait, go on.
Where's
Try
the
this
pointer?
one. I have also one.
We have the pointer. Where is it?
זה עובד.
I don't know why the mouse doesn't show up. Okay.
Quelqu'un est parti avec. Someone took it.
No, it's okay. Oh, okay.
Working?
Nah.
No, it's yeah, it's working.
Oh, brilliant. Thank you. That's awesome. Now we can see the... Well, I see it on mine. You see it?
So maybe it's a presentation.
Yeah, all right. So let's see. Remember two things.
Can, you know,
Oh, that's even better.
like, and afterwards you have to sing something.
All right, no problem. Will this go all the way there? Is this long enough? Oh, wow, I feel like a star. All right. It's all good. All right. I don't know any Israeli songs, sorry. Thank you. All right, so uncinate fasciculus is this guy here. It's a C-shaped white matter tract that goes from the orbital frontal gyrus to the temporal lobe. Okay, I'll show you pictures of this later on. And then there is your inferior longitudinal fasciculus that's in the temporal lobe that goes all the way back. Here you have your arcuate fasciculus that again is a C-shaped white matter tract that goes from temporal lobe up to your inferior frontal gyrus. Okay, but as you can tell, depending on the shape of the white matter tract and where it is, it can look different in color, right? If you have something that's C-shaped, the top part, if it's going back and forth, is going to be green. The vertical part is going to look blue, and then the bottom part is going to look green again, right? So it's not necessary that one tract is going to be one color. And that's represented here. So this triangular thing here, which is also what I'm showing over there, is your arcuate fasciculus. But as it digs down into the temporal lobe, it's going to turn blue now. And then it's going to come back and then become green again, okay? And then your corticospinal tract, which is that blue thing that's going top and down again. Okay. So practically speaking, we have this case where there is a small cavernoma in the post-central gyrus. So central sulcus, pre-central gyrus, post-central gyrus. So we have a small cavernoma here, and this neurosurgeon said, hey, can I just take that thing out because the patient's having seizures? There were some other cavernomas as well in the right parietal white matter, a little bit more, I guess, caudal in the parietal lobe. And so we did, DTI, and then we said, okay, well, I guess you could try to take this thing out, but what's this blue thing? What's going on from top to bottom all the way to the, corticospinal tract? So that's a problem because the lesion is now right behind it. So if he tries to cut into this, he might end up cutting part of the corticospinal tract, right? And then same issue over there. So the surgeon decided, well, there were some more pictures here, I think. So this guy here, then that one he couldn't touch. So what about here? There's a lesion in the parietal white matter, and if he tried to take this out, what's gonna be inflicted here? Optic radiation. Now that's gonna be a major problem too, right? So he decided, okay, he's not gonna do that. So, I think you can probably tell where things are without diffusion tensor imaging. So that's another just coronal image showing it. This is actually kind of interesting. So the other lesion is right next to the arcuate fasciculus as well. So this was a little bit too close for him. So he decided not to operate on those things, and essentially we did radiation. With brain tumor imaging, we like to overlay some of our white matter tracts onto the brain, and then I'll talk about functional MRI later on. But this is a nice example of showing how different activation regions in the brain can be related to white matter tracts and in relationship to brain tumors, basically. So, for example, this one, there's a lesion in the frontal lobe, right? And then this is the uncinate fasciculus that's in blue that he wanted to avoid. Okay, so those are our brain tumor type stuff. And this one, it shows just corticospinal tract, for example, being posteriorly displaced by this lesion in the superior frontal gyrus rather than lateral, for example. Now, what I talked about before was, this infiltration of brain tumors. To me, this is the more fun part daily to try to figure out how you can be a better neuroradiologist. Because I have seen many cases where small lesions were missed because the person was not looking for something in distant white matter tracts, okay? This, there's a lot of literature talking about how diffusion tensor imaging might be able to distinguish between infiltration of white matter or destruction of white matter or edema. In my experience, maybe I'm just not that good at doing this, but I haven't found that it's really easy to tell, okay? But it does affect white matter. So what I mentioned before was infiltrated neoplasm often spread along known white matter tracts, and then it's useful for trying to figure out distant infiltration. So we'll review some of the white matter tracts, okay? If you remember this, fine. If you don't remember this, easily Googleable. But the point is that if you know that these things happen, then now you can find those tracts and then try to look for tumors along that location. So cortical spinal tract, we already looked at, goes from top to the bottom through the brainstem, right? So for example, this was an interesting case where it was a high-grade glioma, and then there's a lesion in the precentral gyrus, a lot of surrounding T2 hyperintensity, which is a mixture of tumor and edema. And when you look lower, these are the initial images, okay? And you don't really see anything worrisome. But an imaging from maybe 4 to 5 months later, you see that little T2 hyperintensity, right, in the posterior limb of an internal capsule. And then you see T2 hyperintensity in the pons, where you expect the cortical spinal tract to be. So this one initially actually was not really called because people maybe were not paying attention to it. Maybe they thought something was artifactual in the posterior fossa. And then several months later, it developed into this. So you actually have enhancing lesions in the cerebellar hemispheres. And they didn't know what this was. We were doing brain tumor conference, and they thought the person had metastatic disease from some other source. And then I was kind of like, well, looking at the images, I said, well, you got this abnormality in the cortical spinal tract, so this must be the same thing. And so they biopsied it, and sure enough, it was that glioma. So now, some of the white matter tracts review. The cingulum bundle goes from the cingulate, it goes along the cingulate gyrus from the front of the corpus callosum all the way to the back, and then eventually goes into the temporal lobes. And this one's really interesting because a lot of people think that Alzheimer's disease, for example, affects this bundle. So if you see a lesion in the anterior cingulate, then look back in the posterior cingulate, or sometimes even in the parahippocampal gyrus, where this connects to. The superior frontal occipital fasciculus, or the IFOF, those are two white matter tracts that go from the front of the brain all the way to the back of the brain. So if you see something in the frontal lobe, make sure you check in the occipital lobe, because things can actually happen that far. The uncinate fasciculus, this one I've seen many cases where there's a lesion in the anterior temporal lobe, and then if you look carefully, there's actually a lesion in the adjacent orbital frontal gyrus, so the bottom front part of the brain, okay, or vice versa. So there's that C-shaped white matter tract that connects those two. The superior longitudinal fasciculus we talked about a little bit, but the arcuate fasciculus is one of them. Depending on who you talk to, people say there's 3, 4, sometimes like 5 different parts of the SLF. The arcuate fasciculus is again the most famous one, which connects Broca and Wernicke from IFG and superior temporal lobe. But there are other tracts that go from superior frontal gyrus to, for example, the inferior parietal lobule. The inferior longitudinal fasciculus, we talked about this before too, it goes from the front of the temporal lobe all the way back to the occipital lobe. So if you see something in the temporal lobe, look back into the occipital lobe, okay? And then probably the most famous one is optic radiation, right? From the lateral geniculate nucleus of the thalamus to the occipital lobe, all right? So just kind of wrapping up here, we will do a quiz. If you saw a lesion in the area in red, which is right next to C, yeah? Where do you need to pay attention to? A, which is the occipital lobe, B, which is lateral occipital lobe, C, which is the contralateral side, or D, which is much anterior. So who says A? Nobody. Huh? Who says B? Nobody. Who says C? Nobody. Who says D? Oh my God, you guys are so good. Did you know this already? Yeah? Okay, sorry. Yes, so which tract is this going to go along?
Cingulate.
Yeah, cingulum bundle, exactly. So this one is a cingulum bundle, right? It connects everything to of the anterior and posterior cingulate gyrus. And again, it goes into the parahippocampal gyrus too, so you want to remember that part. Okay, so just, I think this might be the last quiz. If you have a lesion, no pictures here, just somebody's calling you on the phone and says, hey, I have a lesion in the posterior part of the left orbitofrontal gyrus. Would you see it in the left suprafrontal gyrus, left middle parietal gyrus, right orbitofrontal gyrus, or left anterior temporal lobe, which is called the temporal pole? Who says left superior frontal gyrus? Left middle parietal gyrus? No, because it doesn't exist. There's no such thing as left middle parietal. Right orbitofrontal gyrus, contralateral side? No. Left anterior temporal lobe? Oh my God, you guys are so good. Yes. So this is through what? Which white matter tract was this? Uncinate fasciculus, exactly. So this is your uncinate fasciculus, okay? So again, next time you see brain tumor, high-grade glioma, infiltrating gliomas, check where it is, and then check your white matter anatomy, and then try to find things along that track, because I guarantee you that you're going to start finding things that are farther out that people have not noticed. So, in conclusion, DTI is awesome, and it's useful for pre-surgical brain mapping, again, giving information to the neurosurgeon so they can avoid important eloquent tracts. And I think the more important thing daily is that it aids in prediction of infiltrated tumor spread patterns. Right? Thank you very much. Sorry for all the technical trouble.